In this video, we will learn about integer and rational number exponents. So beginning with integer exponents, we start off with anything to the 0 power. And anything to the 0 power will always equal 1. It could be a variable such as x to the 0 power, that will equal 1. It could be a number like 245 to the 0 power, that would also equal 1. It could be a fraction to the 0 power, so like 1/2 to the 0 power, that would still equal 1. Next we have negative exponents. So here we have x to the negative n power. Negative exponents does not mean a negative number, but what it means is that we have a fraction. So what we do is we put 1 over, and then we do x to the positive n power. So for example, if we had 2 to the negative third power, we could write that as 1 over 2 to the positive third power, and 2 to the third power is 8, so that would equal 1 over 8. Now what if we had 1 over a negative exponent? So here we have 1 over 2 to the negative third power. Alright, so what we have is with this negative exponent, okay, this means 1 over. So what we have, showing this the long way, we would have 1 over 2 to the third power. Right, because that bottom part is the 1 over 2 to the third. And what that does is when you divide by that fraction, we have 1 times, you multiply by the reciprocal, which would be 2 to the third power, and that would be 2 cubed, which would be 8. So that's kind of the long way. The short way is realizing that the negative exponent, if it's in the numerator, such as over here, it'll bring it down to the denominator, as we see right here. And then if it's already in the denominator, the negative exponent will move it up to the numerator. So we have 2 to the positive third power on the top, which again, that would equal 8. All right, so the only time we're moving from top to bottom would be with the negative exponents. And that's only the part with the negative exponent that we're moving. So if there was a combination of negative and positive exponents, only move the parts with the negative exponents. Another example, we have 4/5 to the negative second power. So the short way of thinking through this is realizing that the negative exponent would basically switch things around. So the short way would be realizing that this would be 5 over 4 to the positive second power. The longer way of thinking of this would be realizing that the negative exponent, whatever exponent you have, really, will go with both the numerator and denominator of the parentheses. So what we would have is 4 to the negative second power over 5 to the negative second power. And the negative exponents moves those parts. So up here, this would go to the bottom. And then because this is a negative exponent, that goes to the top. So we have 5 squared on the top, 4 squared on the bottom, which is what we have, right? So we have 5 over 4 squared would be the same thing as 5 squared over 4 squared, which would be 25 over 16. So your final answer is 25 over 16. So this up here was the longer way. The shorter way is realizing the negative. We'll simply switch the numerator and denominator, and so we have 5 over 4 squared. Now before moving on, I just want to touch on the 0 exponent for one more moment. Okay, so realize that if we have 0 to the 0 power, that is undefined. Okay, this is undefined. All right, that has no solution. And then also, if we have 0 to the negative n power, that is also undefined because 0 to the negative n power would be the same thing as 1 over 0 to the n power, and 0 to any power, whether it be to the 4th, 5th, 6th power, whatever, it's going to be a 0 in the bottom. So what we have with this expression here is 1 over 0, and anytime 0 is underneath in a fraction, that would be undefined. So if it's underneath, it's undefined. It sounds kind of similar, underneath, undefined, so that's a way to remember that. If a 0 is on the top, by the way, it's fine. So if you have 0 over 5, for example, that would just equal 0. So if it's on the top, it's 0. If the 0 is on the bottom, it's undefined. So this here we've dealt with zero exponents. We've also dealt with negative exponents. And now we're going to deal with some properties of exponents. So first we have the product property. And that says that if you're multiplying when you have the same base, okay, then you would have to add the exponents. So here we have x to the m power times x to the n power. We would add the exponents m plus n to get your exponent. And then if you're dividing, instead of adding the exponents, you would have to subtract the exponents. So here in this example, if you have x to the m over x to the n, we would subtract the exponents. So we get x to the m minus n. And then we have a power property, which says if we have a power to a power, so x to the m power raised to the n power, you'd have to multiply the exponents, m times n. So what this would look like with an actual example, here we have this expression, and we're trying to simplify. All right, so looking first off at the numerator. Okay, we have here this parentheses raised to the fifth power. So what we do is we raise each part here in the parentheses to this fifth power. So we have 2 to the fifth power. So we have 2 times 2 times 2 times 2 times 2. That would be 32. Then we have x cubed to the fifth power. Power to a power, our power property, says we multiply the exponents, 3 times 5 to get 15. So that's x to the 15th power. And then y squared to the fifth power. Again, power to a power, so we multiply 2 times 5 to get 10. So we have y to the 10th power. And then that's over, here x to the 9th, y to the 11th, and then z. So we can take this further. So the numerator, 32 is by itself. That does not simplify with anything else. But look here with the x's. We have x to the 15th power, divide by x to the 9th power. We would subtract the exponents, because that is our quotient property. We subtract 15 minus 9, and we get x to the 6th power. And that goes on the top because 15 is larger than 9, and 15 was on the top. And then here, for the y's, so again, we can subtract the exponents. We subtract 11 minus 10 to get y to the first power. And that goes in the bottom because 11 is larger than 10, and 11 was in the bottom. All right, so there's more y's in the bottom, so when you simplify, what's remaining would be in the bottom. And then z is by itself. That is not combined with anything, so that just goes down there. So your final answer is 32 x to the 6 over y to the first times z. And we don't need to write the 1 here. You can just write that as y times z. All right, so you just erase that if you want and write it like this. Now, an application of exponents, whether it be positive or negative exponents, is in the context of scientific notation. All right, so this is useful when working with large numbers or really small numbers. So our first example with scientific notation is the number 2,300,000, which this is not a really huge number, but it's we don't want a really massive one for our example because it's going to be more difficult to deal with. But here with this example, what we're trying to do is write this in a shorter way. All right, so all these zeros, our objective is to not need to write all those out. All right, so what we do is we want to put our decimal point, we want to move it, so right now it's here at the end, it's assumed to be here, and we want to move it after this first number, this first non-zero number. So we move it over there to get 2.3. And then we write this as 2.3 times 10 to some power. Now the power we raise it to is determined by how far our decimal point is moving. So it's going from here over 6 places. You can count that out, right? 1, 2, 3, 4, 5, 6 places. So that would be 2.3 times 10 to the 6th power. All right, so this would be written in scientific notation. If you had a smaller number, let's say something smaller than 1, such as right here, this 0.000467, again, we want to move the decimal point from here after the first number that's not 0. So it goes right here after the 4 to get 4.67 times 10 to some power. Now in this case, our decimal point is going over 1, 2, 3, 4 places. So this would be a 4 up here, but it's going to be a negative exponent because this number is smaller than 1, right? The 0.000467 is smaller than 1. So we need to write this with a negative exponent because negative exponent, remember, means 1 over. So that would be 1 over 10 to the 4th power, which is a fraction, meaning it's going to make this number smaller when you multiply it by that fraction. All right, so make sure you can convert back and forth between these two expressions, whether it be a large number or a small number. And take note that on your calculator, if you're doing different calculations, if you see right here 5.3 and then E10, many calculators will write it like this. And what that means is the same thing as 5.3 times and then 10 to the 10th power. So this E is another way of writing 10 with this exponent. All right, so if it was like, let's say 4.7 times 10 to the 8th power, your calculator would write that as 4.7 E, which means 10 to some power, and then it would be E8. That means 10 to the 8th power. All right, so take note of that when you're doing different calculations on your calculator. All right, so we've dealt with zero exponents, positive exponents, negative exponents. Next, we're going to work with rational exponents, meaning a fraction. Now, if you have a fraction for an exponent, that actually can be converted into a radical. It's like a square root or a cube root or a fourth root, something like that. So for example, if you have x to the 1 over n power, so this fraction is now your exponent, what that means is it can be written in the following way. Okay, the fraction means it's going to be a radical. The x would go inside. This 1, the numerator, would go in here as the exponent. And the n, whatever is your denominator, would be your index. All right, so you can write that like that. And we see it typed up right here. So another example, if you had 8 to the 1/3 power, you can write that as a radical. The 8 goes inside. The numerator goes with the 8. The denominator is your index. So you can write that as the cube root of 8. And the cube root of 8 would be 2, because 2 cubed is equal to 8. All right, and here we see if you have something other than 1 in the numerator, still the same process. So for example, if you had 16 to the 3/4 power, again, the 16 would go on the inside, the 3 goes with the 16, and the 4 would go out here. So we have the fourth root of 16 to the 3rd power. And actually, another way you could write this, and this would be okay as well, would be the 16 goes here, the 4 still goes here, but the 3 could go on the outside if you want. So it could go like this. And it doesn't matter which way you do it, it just depends on what's easier. Because if you do it this first way, 16 to the 3rd power is going to be some really large number. And you could do this on your calculator, but if you're trying to do it by hand, you want to maybe make it into a smaller number, and that would work better if you use the second approach. So we have the fourth root of 16, so what to the 4th power equals 16? It's going to be 2, right? 2 times 2 is 4, times 2 is 8, times 2 is 16. So that would be 2, and then raise that to the 3rd power after. So 2 to the 3rd power would equal 8. So your final answer is equal to 8, and it's either way you get the same answer, going the first approach or the second approach, but depending on the scenario, one might be easier than the other. Now, still on the topic of radicals, here we're trying to define this expression. All right, so you have the index is n, you have x to the n power. All right, so we want to look at two scenarios. One if n is even, and then the other is if n is odd. So if n is even, we would say that the nth root of x to the n power would equal the absolute value of x. And if n is odd, then we would have the nth root of x to the n power is equal to x. So what is the difference between these two things? Well, let's take a look with an actual example. So let's say here we had, let's do the fourth root of 2 to the fourth power. That was an ugly 2, but we can get the idea. Here, 2 to the fourth power would be 2 times 2 times 2 times 2. So that'd be 4, 8, 16. And then the fourth root of that would equal 2, right? Now what if we had the fourth root of, let's say, negative 2 to the fourth power? So negative 2 to the fourth power would be 4 negatives, which makes it a positive still. So still a positive 16, and a fourth root of that would still equal 2. Now let's compare that with to the third power. So if n is 3, so if you have a cube root of 2 to the third power, okay, 2 to the third power is 8. The cube root of 8 is 2. Whereas if we had the negative 2 to the third power, that would give you a cube root of negative 8, which would be negative 2. So notice the difference. Okay, so here in this example, if n is even, it doesn't matter if you have a positive or a negative on the inside, your final answer would be a positive number. It's going to be the absolute value of whatever you put in here, right? Absolute value of 2 is 2. Absolute value of negative 2 is still positive 2. Whereas down here, if n is odd, whatever number is here, so whether it be a 2 or negative 2, if the exponent and the index is odd, okay, it's going to be different because positive 2 would still be positive 2. Negative 2 here, you'd have a negative 2 as your outcome. All right, so if it's even, the x is going to be the absolute value, whereas if it's odd, it's going to be whatever the number was originally. Now, this is important when you are dealing with variables. All right, so for example, if you had this example, you have the fourth root of 81 to the times a to the fourth power. Okay, the fourth root of 81 would be 3, because 3 to the fourth power is 81. All right, and then here, a to the fourth power, if you take the fourth root of that, okay, the 4 and the 4 will basically cancel out. You're left with a. Okay, but it's important to indicate that this is going to be the absolute value of a, because a is an unknown number. It could be a negative, it could be a positive. We don't know what it is, but whatever it is, we need to take the absolute value, right? Because if it's a negative 2 to the fourth power, right, if a is negative 2, it's going to be a positive 2. It's going to be an absolute value of that here for the variable. And we've indicated that over here with this first example. And then for this second example, if we had the cube root of 27 times b to the third power, okay, the cube root of 27 would be 3, because 3 cubed is 27. And then here we have b cubed, and we're taking the cube root of that. So if the exponent and the index are the same, that will cancel out. You're left with just the b. And it doesn't matter what b is, because it will still be the same sign no matter what, because n is odd. Right, we verified that over here. So in this case, we don't need to put the absolute value symbol because we don't need it, because n is odd, because of the 3 and the 3 here. So this can just be written as 3 times b. So again, the only time we need the absolute value symbol is if n is even, such as a 4 and a 4, and we're dealing with variables. Now, continuing the topic of radicals, we have 3 different properties we want to discuss. So we have the product property of radicals, quotient property, and then we have the index property. And we see it all listed here with variables. So let's kind of walk through what each of these mean. So here, with the product property of radicals, if we notice that if the radical is the same, such as right here we have a nth root, here is an nth root. If the roots or the index are the same, we can combine into one radical by multiplying, in this case, x times y. What that would look like would be something like this here. If we have the square root of 3 times the square root of 27, we can combine into one radical because they're both square roots. And that would give you 3 times 27, or the square root of 81, which in turn would equal 9. Or if you had, let's say, the cube root of 3 times the cube root of, let's say, 9, you can combine because the index both are the same. It's both a cube root. So those can combine. That would give you the cube root of 3 times 9, which would be 27, and that would in turn be 3. All right, so the index or the indices must be the same to combine when multiplying. Same thing with dividing. Okay, that's what we have here for the quotient property. Let's use an actual example. Let's say we have the square root of 27 divide by the square root of 3. Okay, those can combine because those are both square roots, and we do 27 divided by 3, which would be 9. And square root of 9 would be 3. And again, that would still apply if you had, let's say, the cube root of 9 divide by the cube root of 3. Those could combine as well because those are both a cube root. Those are like terms, so to speak. And so this can combine to get a cube root of 9 divided by 3, which would equal 3. So that would be the cube root of 3. And now this third one is probably new for you, and it looks maybe kind of weird. So let's explain this with an example. Let's say we had the, let's do the third root of the square root of, let's make it 81. So what that means, a square root, by the way, has an assumed index of 2. So what that means is we can combine this. So 81 would still be the number on the inside, but we put this into one radical by multiplying 3 times 2 to get 6. So this would be the 6th root of 81. Now if you're wondering why is this true, let's take a moment to explain. All right, so looking here, if we have this expression, remember we can write this as with a fractional exponent. So this can be written as x, and then this would be 1. It's an assumed 1. That's your numerator, and then m would be your denominator. So you have 1 over m, and that would be your expression. And then that is taking the square root, or the nth root of that. All right, so this would be x to the 1 over m power, and then taking the nth root of that. All right, so again, we can write this as x to the 1 over m, and then this n here, we can combine because this would be your numerator, and this here would be your denominator. So we have 1 over m, and then over n, which would be divide by n. So you divide by n, that's the same thing as taking 1, or multiplying by 1 over n, which would give you x to the 1 over m times n power. And then put it back as a radical. So you have a radical, x would be on the inside, 1 would be your numerator, that goes right here, and then mn would be your index. So mn. So we have just verified that that radical over here is equal to the m times n root of x. So all that is the behind the scenes of why this property is true. Now we're going to work with those properties, and we're going to simplify different radicals. So when you're simplifying radicals, the radicand, which is the number inside of the radical sign, needs to contain only powers less than the index. So for example, if you had here a square root of x cubed, what you want to do is make this so that this index, or this exponent, sorry, is less than the index of 2. So different ways you can think through this. The way I kind of prefer is thinking through this as 3 x's on the inside. And then whatever the index is, you're going to look for groups of that number of items. So the index is an assumed 2, it's a square root, so we're looking for groups of 2 items. Here's a group of 2 x's, which means for each group we pull out one of those. So we have one group of x's, we pull out one x, and you're left with an x on the inside. So x on the outside, one x is left on the inside, and we see that typed up right here, but notice that we have an absolute value symbol around the x that we brought out. And the reason is because this number here, this exponent, is an odd number. So we have to account for that, and so the absolute value symbol would go around that. Now this next example, here we have the 8th root of x squared. All right, now in this case, we can actually simplify this a little further. Even though we can't pull anything out, we can actually make this simpler. And the short of it is we can actually just divide the 2 by the 8 to get 1 and 4. So this can be written as the 4th root of x. And the reason why that works is because we can rewrite this radical right here. We can write that as a fractional exponent. So we have the 2 right here would be your numerator, and then this 8, the index, would be your denominator. So we have x to the 2 over 8 power, which is x to the 1 over 4 power, which if you convert that back into a radical, we have a radical, x goes on the inside, 1, the numerator, is your exponent, and the 4, the denominator, is your index. So that is why we can write this as the 4th root of x. Now a third thing to take into account when simplifying is that there should be no radicals in the denominator. So here we have 1 over the square root of 3, and we need to what we call rationalize this radical. So we need to get rid of the radical in the bottom by multiplying by something that will eliminate it. So for a square root, we would want to multiply by the square root of 3 on the top and on the bottom. When you multiply the numerator, we have 1 times square root of 3, which is the square root of 3. And the denominator, when you have the square root of 3 times the square root of 3, that gives you the square root of 9, which would be 3. So this can be written as the square root of 3 over 3. And we see that typed up right here. Now if you have a cube root in the denominator, again you need to get rid of the cube root by multiplying the top and the bottom by something. Cube root is going to be a little bit different because with the cube root, to eliminate the radical, we need 3 items to pull out. So like for example, if you look up here, if you have the cube root of 3 times 3 times 3, all right, we have 3 3's on the inside. Because of that, okay, 3 3's is what's needed to eliminate or to pull something out because the index is a 3. If it was a 4th root, we need 4 3's. 5th root, we need 5 3's. But because there are 3 3's, we can pull out a 3, and you're left with nothing on the inside. Your answer is 3. So we need 3 3's, all right, inside the radical. Here we have 1 already on the inside. We need 2 more, right? Because when you do that, looking at the bottom, we have the cube root of 3 times 3 times 3. We put it all together, which gives you 3 on the bottom. But again, do the same thing on the top, multiply by the cube root of 3 times 3, which is the same thing as 9, right? 3 times 3 is 9. So the top would be the cube root of 9. So your final answer, when you simplify, is going to be the cube root of 9 over 3. And we see it typed up right here. Now, again, with fractions, okay, we don't want radicals in the bottom, and we do not want a fraction itself under a radical. So for example, we do not want the square root of x over 3 inside the radical. We do not want this denominator, specifically this 3, inside the radical. So what we can do is we can separate this. We can write this as the square root of x over the square root of 3, and then we can eliminate the radical in the denominator by multiplying top and bottom by that square root. So we can have on the top the square root of 3 times x, and the bottom we would have the square root of 3 times the square root of 3, which would equal 3. So this here would be your final simplified answer. So we have just dealt with the simplifying of radicals, and next we want to work with the operations with radicals. So that would be addition and subtraction, as well as multiplication and division. Now for addition and subtraction, okay, when you're adding and subtracting, we must have like radicals. So it must have the same radicand and the same index. So this is the same idea as adding and subtracting like terms, right? If you had, let's say, 3x plus 5x, we can combine because those are like terms. They have the same variable component, and that would give you 8x. Now instead of x, in this case, we are replacing it with an actual number. The number is the square root of 2. So here we have a comparable example. Instead of x, we have square root of 2. So here we have 3 square roots of 2 plus 5 square roots of 2. That gives you a total of 8 square roots of 2. So notice how that compares. Instead of x's, we have square roots of 2's. So that's with addition and subtraction, same idea. And again, the index must be the same as well. So they must both be, square roots or cube roots. They must have the same index. Now for multiplication, we also need to have the same index. Okay, so here, for example, we have 3 times the square root of 2 times 4 times the square root of 3. Now when you're multiplying, remember, it does not matter the order of multiplication. So we could multiply 3 times 4 first to get 12, and then multiply the square root of 2 times the square root of 3 next. And you can multiply those because they're both square roots. They have the same index. And you multiply 2 times 3 to get 6. So your simplified answer would be 12 times the square root of 6. And then the same rules apply for division. So let's say we had, let's make it 8 times the square root of 4, divide by, let's make it 2 times the square root of 2. Okay, we can divide in the same manner. The number part, without the radical, we can divide like normal. 8 divided by 2 would be 4. And then square root of 4 divided by the square root of 2, we can divide those. 4 divided by 2 gives you 2. So we have the square root of 2. So your final answer would be 4 times the square root of 2. Now to finish off this lesson, we're going to look at just a couple examples where we are going to apply the concepts we have learned. So first off, we have 3 times the square root of 2x minus the square root of 8 times x. All right, so right now, nothing can actually combine, nothing can simplify, because these here are not like terms. They're not like radicals. But notice the 8 here. So if you look at the square root of 8x, okay, 8 we can factor down as 2 times 2 times 2. Then we have an x also inside. And because we're taking a square root, we can look for groups of 2 items. And so here we have 2 2's. So we have one group of 2's. So we pull out 1, 2. So we pull out a 2. We're left with a 2 times x on the inside. So this square root of 8x would be converted to 2 times the square root of 2x. So now we have this new expression. And now notice we do have like terms. We have like radicals, the square root of 2x and the square root of 2x. So those can combine these terms by subtracting 3 minus 2. That gives you 1. So we have one of those, and we have 1 the square root of 2x. So your final answer would simply be the square root of 2x. We don't need to write the 1 in the front. Here is another example. So in this case, we have 3 times the square root of 3 plus 5 times the square root of 3 minus 4. Now for this one, we need to distribute, or FOIL is another term we can use, because we're going to distribute this 3 square root of 3 by multiplying to this term over here, and then we multiply by the negative 4. So we distribute to both terms, and when you do that, 3 times square root of 3 times square root of 3, we have the square root of 3 times square root of 3 is the square root of 9, which would be 3, right? And then we have that times negative 4. 3 square root of 3 times negative 4 is negative 12 times the square root of 3. And then we want to distribute this 5 to both terms. So we have 5 times the square root of 3, and then 5 times negative 4, which gives you negative 20. All right, so now we can combine like terms. So here we have 3 times 3, which is 9, minus 20 gives you negative 11. And then negative 12 squared root of 3 plus 5 squared root of 3. Those are like terms. And we have negative 12 plus 5 gives you negative 7. So we have negative 7 times the square root of 3. All right, so this here would be your final answer. And we see that all typed up right here. So again, this is your final answer. Let's take a look at 2 more examples. Here we have this one, and different ways we can approach this, but the main issue at the moment is we do not want this radical in the denominator. So we have a square root in the bottom. So to get rid of the square root, we can multiply top and the bottom by the square root of 6. So on the top, when you combine, when you multiply the numerators, we have the square root of 3 times the square root of 6. That gives you the square root of 18. So we have 3 times the square root of 18 on the top, and the bottom, the square root of 6 times the square root of 6 would be 6. Now the square root of 18, let's take a look at that for a moment. That can actually simplify further, because 18 can factor down as 9 times 2, and 9 is 3 times 3. So that would be 3 times 3 times 2. Here we see a group of 3's that we can pull out. So we pull out 1 3, and you're left with a 2 on the inside. So that would be 3 times the square root of 2. So we have a 3 in the front already, times that 3 square root of 2, and that's over 6. So on the top we have 3 times 3, which is 9. So we have 9 square root of 2, divided by 6, and then this can simplify one last time. 9 divided by 6, you can divide both by 3. That gives you 3 on the top, and then 2 on the bottom. So your final answer is 3 times the square root of 2 divided by 2. And we see that all typed up right here. Now, by the way, another approach we could have done is if you take a look at the original problem right here, we can see that these two radicals can divide out. Divide top and bottom by 3, we get 1 and 2. So you have 3 times the square root of 1, which is 1. So you have 3 times 1, or 3 on the top. The bottom would just be the square root of 2. Multiply the top and bottom by the square root of 2. That would be 3 square root of 2 on the top, and then 2 on the bottom. So notice 2 different ways to approach that, but either way, we get the same final answer. Now, one more example. Here we have 5 over 3 plus 2 times the square root of 2. Okay, this one we've not directly talked about in this lesson, but we're going to explain how to do this. So this one's a little different because our issue is the square root of 2 in the bottom, right? So that's not really anything new, but what's new is the fact that we now have 2 terms in the bottom. We have 3 plus this 2 square root of 2. So you could just try to multiply top and bottom by the square root of 2, but that's not going to work because all that's going to happen, and you can try this to verify, but all that's going to happen is the square root of 2 would move to the first term over here and not really change anything. All right, so to do this, we need a different approach. So the approach, whenever you have 2 terms in the bottom, where 1 or more has a radical, you can multiply the top and the bottom by something. But in this case, what you do is you multiply top and the bottom by the conjugate of this denominator. So instead of 3 plus 2 times the square root of 2, multiply top and bottom by 3 minus 2 times the square root of 2. So all you do is you change the sign right here. So if this were minus originally, you'd have to multiply by 3 plus. But because it's a plus, multiply by 3 minus. And do that on the top and the bottom. So on the top, make sure that you are distributing this 5. So 5 times each of those terms. 5 times 3 is 15. 5 times negative 2 times the square root of 2 would be negative 10 times the square root of 2. And then the bottom, we'll do this up here with a little more room. We have 3 plus 2 times square root of 2 times 3 minus 2 times square root of 2. When you distribute, 3 times 3 is 9. And then 3 times negative 2 square root of 2 is negative 6 square root of 2. And then distribute this 2 square root of 2 to both terms. So 2 square root of 2 times 3 is 6 square root of 2. 2 square root of 2 times negative 2 square root of 2. 2 times negative 2 is negative 4. Square root of 2 times square root of 2 is 2. So we have negative 4 times 2, which is negative 8. So notice what happens. These two middle terms will cancel out. You're left with 9 minus 8, which would be 1. So notice the radical is gone, and the bottom is going to be a 1 in this case. And then anything over 1 is just what you started with. So we're going to have 15 minus 10 times the square root of 2 as your final answer. All right, so again, the key is multiplying the top and the bottom by the conjugate in this case to get rid of that radical. And that concludes our lesson for today. We will see you next time.